We can now look at large signal characteristics of an NMOS common source amplifier loaded by a PMOS active load. So we have an NMOS transistor Mn biased at a gate voltage VGN and a PMOS transistor MP biased at a gate voltage VGP. The supply voltage is VDD. And to the NMOS transistor, we apply an incremental voltage Vi. At the output, the operating point voltage is VO bias and there is an increment of VO. We consider this entire input to be the large signal input Vi and this entire thing to be the large signal output VO and plot VO versus Vi. We do this by plotting the characteristics of the NMOS and PMOS transistors with these variables I and VO. Okay. So we have the I versus VO axis on which we plot the characteristics of both NMOS and PMOS transistors, and from that we plot V0 versus Vi of the entire circuit. Now in this case, the PMOS transistor has a fixed gate voltage, so a fixed source gate voltage VSG, which is equal to VDD minus VGP, and its source drain voltage, this voltage is VDD minus VO. And the NMOS transistor has a gate source voltage equal to the input voltage Vi and a drain source voltage which is the same as the output voltage VO. Okay. Now first, the PMOS transistor, it has a fixed source gate voltage, so it has a fixed ID versus VSD characteristic. It's like this. Okay. Now we know that the VSD, source drain voltage of the NMOS transistor, is nothing but VDD minus V0. So the same characteristics on the I versus V0 plane will be exactly the same thing but reflected about VDD. So it will have a characteristic like this with some saturation current. Okay. So this is for PMOS, for VSD equal to VDD minus VGT. Okay. Now let's start with Vi being very small, let's say equal to 0. If it is 0, this NMOS transistor is off because its gate source voltage is below the threshold voltage. In fact, as Vi increases, as long as it is below the threshold voltage, the NMOS transistor is off and the current is 0. Okay. In fact, that characteristic corresponds to just a 0 current line here. So this is for NMOS with Vi less than VTN. Okay. Now if this current is 0, you can see that the point of intersection is at VDD. So that is, this node will be at VDD. A transistor that is on can carry a zero current only if its source drain voltage is zero. Okay, so the voltage across the PMOS transistor is zero and the output voltage is at VDD. So for Vi from 0 to VTN, the output voltage will be equal to VDD. Now, as Vi increases a little beyond VTN, the characteristic of the NMOS transistor looks like this. Vi slightly more than VTN. The point of intersection will be close to VDD but less than that, okay, because the PMOS transistor curves to the left. So it will be slightly less. And as the value of Vi increases, the points of intersection keep moving to the left. So we'll have points like this. Okay, and we can see that in these cases PMOS transistor is in triode region and the NMOS transistor is in saturation region. Now at some value of Vi, both NMOS and PMOS will be in saturation region, that is, they intersect in the flat region of the characteristic, nearly flat region. So again, when we have nearly flat curves intersecting each other, a small movement in each of them moves the point of intersection by a large amount. So in this case, a small change in Vi changes the output voltage by a large amount. And after that, for values of Vi beyond that, what happens is the NMOS transistor goes into triode region, okay, and the PMOS transistor will be in saturation region. So the value of the output voltage goes on falling, but it never quite reaches zero, because as Vi increases, this voltage keeps falling and eventually the NMOS transistor is in triode region. Now, because some current has to be flowing there, there has to be a non-zero drain source voltage across the NMOS transistor. So the output voltage never quite reaches zero. Okay. So the output voltage goes on reducing, but even if we set the input voltage to be equal to VDD, the output will not be exactly zero. It can be close to zero. That depends on the parameters of the two MOS transistors. So it looks like this, and for Vi equals VDD, this is what it will look like. You can see that this is the opposite of what happens in a PMOS common source amplifier with an NMOS active load. In that case, the output was reaching zero exactly, but not VDD, and here it is the other way around. Okay. So again, in this part, we have PMOS in triode, NMOS in saturation region, and in this part the other way around, PMOS in saturation and NMOS in triode, and in the middle both are in saturation region. Okay. So this is another similar circuit, except that the roles of NMOS and PMOS are reversed.